This is lecture 10, fractals. So first we have to talk about cardinality of sets and how do we say what sets have more or less elements. So let's consider the set n being the natural numbers. So you all know that this set is 1, 2, 3, 4, etc. So that's the natural numbers. So let's begin with that. So how many elements does this set n have? Infinitely many, right? Now, let's think of the positive integers. So sometimes this is just defined as the natural numbers, and other times it's defined with a 0. We're going to just define it with a 0. So let's think about that set. So how many elements does that set have?
Infinite.
Okay, so do you think, say, this has more than this, or do you think they have the same amount? They're both infinite, right? But does one of them have more?
Z positive has one more. Contains 0.
But what's 1 plus infinity?
Infinity plus 1.
Well, okay. Infinity plus 1 is still infinity, right?
Yeah.
So, no, it's okay if you joke. We like jokes in this class. So we can't really, it's not quite certain if this has more than this or if they have an equal number of elements. Or maybe this has more than this. We don't know. But let's think about finite sets first. So we know, say, apples, oranges, or rather, I should probably say an apple, just to make it clear that it's one, an orange, and say a banana. I don't know how to spell banana, but I think it's this, right? Yeah. And then you can have, say, let's think of another type of set. Let's think of colors. So you can have red, orange, and yellow. So if you're comparing those two sets, it's very easy to see that they have the same cardinality. They both have 3 elements. So the cardinality of both these sets is 3. So it's very easy to compare finite sets. Not so easy to compare infinite sets, right? But now let's think of this. Let's come up with, so let's keep this set, but let's also include this set. So red, orange, yellow, and say green. So it's clear to see here that this set is bigger than these two sets. Now why is that? Let's think of it in terms of math. Well, what sort of correspondence do you see here that you don't see between, say, these two sets and this set? So do you see how we can represent this mathematically? Say, using a function. So how, yeah?
No, I was going to say, would it be a series?
Not quite a series.
You said it's like 1-to-1 correspondence?
Exactly. So here you have a 1-to-1 correspondence, right? So you can go from apples to red, orange to orange, and banana to yellow, right? And here, this is just, they're all F, right? So it's just F of apple equals red. F of orange equals orange. F of banana equals yellow, right? There you have a 1-to-1 correspondence. But now, here you can, so if you go from this set to this set, you can go from apple to red, orange to orange, banana to yellow, but then you don't have anything going to green. So there you don't have a one-to-one correspondence. That green is left over, right? So that's the idea. So two sets are set to have the same cardinality if you can create a function with a one-to-one correspondence. But if you can't, then they don't have the same cardinality, right? So that's the idea of cardinality. I don't know if I actually give this definition. Nah, I don't give that definition. But let's just think of these two sets then. So these two sets are infinite, but is there a one-to-one correspondence between these two sets?
No, right?
And if you want it to be.
Okay, or rather, think of a one-to-one correspondence for this, or a counterexample.
Here's 1 to 1.
But what's a correspondence then?
1 to 0, 2 to 1, 3 to 2, 4 to 3.
Okay, we can do that. So let's write it down mathematically. Let's take f from n to z plus, but we can also go the other way around. So it doesn't matter which way we go. But let's take f from n to z plus. Then what is f though? So let's say, so let's call it this. Let's say the elements in z plus are z. So z equals f of n. That's how we want to set up that function, right? So let's say f goes from n to z plus, so that means some z in z plus and some n in n, for some n in n, we're going to have z equals f of n, right? But what's this f of n?
N minus 1.
N minus 1. So this equals n minus 1. We know that n minus 1 is 1 to 1, right? It's actually 1 to 1 and on 2. So n minus 1 is 1 to 1 for these two sets. So we have a 1 to 1 correspondence. So there we found a 1 to 1 correspondence. Now let's think of the real numbers. Or we can even think of the unit interval, say from 0 to 1. Now, can we find a 1-to-1 correspondence between numbers in, say, n to numbers in 0 to 1? So let's think of it this way. How do we represent some x over here? So let's take some x from 0 to 1. How would we represent that?
N is equal to 1 over n. I mean, f of n equals to 1 over n.
That wouldn't quite work, right? Because if f of n equals 1 over n, let's say you have, let's see. Let's say you have 1 over pi, right?
Okay.
Is pi in the naturals? No, right? So that won't work. So let's think of x here. X is going to be 0 point something, right? So say a1, a2, a3, etc., right? So and then let's write in ak, and it goes on. And it has infinite strings of digits, right? So these digits are represented by the natural numbers. So every single a are natural numbers. So these digits can be represented by the natural numbers. So it's not, so obviously we showed that it can't be, or we didn't show, but we can show that it can't be 1 to 1. So here, there's a method to prove that it's not 1 to 1. So basically what you do is you assume that you can go from the naturals to the unit interval, and you have a 1 to 1 correspondence, but then you try to construct that 1 to 1 correspondence, and you see that you failed. But that's a proof for an analysis class, but what I wanted to show you here is that you can't really have a one-to-one correspondence, and you're going to see because these digits are made up of the naturals, the cardinality of this is actually going to be 2 to the power of the cardinality of the natural numbers. But that's a topic for an analysis course. We're not going to really concentrate too much on that. But now let's show that we can go from the unit interval into the real number line. So let's say we want to create a one-to-one correspondence like this. So this is going to be 0 to 1. And we want to go to the real number line. So what function can we use for that? So let's say this is, let's say it's some y in the real numbers, and this is f of x. So let's come up with a function that can do that. And it's actually probably easier on negative one-to-one, I think. So this is going to be, let me just think about this. Maybe this doesn't work out as nicely as I wanted to. So can we get 0 for this? No, that's not going to work. Let's see. We can have 1 minus 1 over x, then that's going to be 1, so that's going to be 0 there, but then that goes to minus infinity. Yeah, this is a bit trickier than I initially thought it would be. In any case, we can find a one-to-one correspondence between 0, 1 to r, but I'll have to think more about that. I thought I would have an easy, so this is what I was thinking of. I was thinking f equals 1 over x, but that doesn't quite work because so this, I mean, this will, the 0 will take it to infinity, but then we start off at 1. So really this goes from 1 to infinity. So it only doesn't cover the entire real line, but still, I mean, this seems like a very different set from this, right? Here you have numbers that are going off to infinity. Here you have numbers that are between 0 and 1. But still you can come up with a one-to-one correspondence between the two. So the cardinality of this is the same as the cardinality of this. But for the real numbers, it needs to be a little different. So let's not concentrate too much on that, because I don't want to talk too much about cardinalities. So I'm going to give you a definition here. So this is going to define what it means to be, say, with this cardinality or with this cardinality. So a set S is said to be countably infinite So they call it countably because you can actually count it, right? So if you take the natural numbers, you can count 1, 2, 3, 4, etc. But if you take the reals, or if you take the unit interval, you can't count it. You have 0, but then what's the next one after 0? Well, you can't really come up with it, right? There's something that after 0, but you can't, it's going to be, 0.0, and then that continued, but then the last one is going to be 1, but that's infinitely far away. So you can't count with these numbers, but you can count with these numbers. So you can count 1, 2, 3, 4, etc. So that's why it's called countably infinite. So this is countably infinite if there is a one-to-one course or one-to-one function from n to S. So that basically means that we could write the elements as a sequence. So here we can come up with a sequence that for z plus, but that sequence is just n minus 1. So if we can write the elements as a sequence, we have one-to-one correspondence between the naturals and S. So that's what it means to be countably infinite. So before we define what uncountably is, or an uncountable set is, let's think of the infinite hotel. So this is kind of like the infinite hotel. So let's say you have an infinite hotel, and every room is booked, right? Every room is occupied. But then you have a guest that comes in. Let's say he's a very important guest, and he wants to get a room, and he asks if they can make a room available for him. Now, is it possible to make a room available for him if every room is occupied, but it's an infinite hotel?
Yes.
Yes.
Okay, how do you do it?
You slide everyone up.
So you slide everyone up if you're countably infinite. So if you have a countable infinity, you can just use this. You can use this trick and just slide everyone up, right? So you move people in room 1 to room 2, move people in room 2 to room 3, etc., etc. And then you put that guy in room 1. But that works if it's countably infinite. It doesn't quite work if it's like this, though. You can't slide things one place, because there is no one place, right? Between any two numbers, you can find another number. So there is no another place. So you can't be sliding people here, because if you slide, then you get rid of infinitely many. So that's what it means to be countable, or countably infinite. So this definition kind of puts everything together. So a set S is said to be countable if it is either finite. So finite sets are also said to be countable because we can count, right? We can count apples, oranges, bananas. So we can count them. So either if it is either finite or countably infinite. Otherwise, it is said to be uncountable. So that's what uncountable and countable are. But now let's think of sets that aren't so easy. So let's keep these here, but let's think of the set of rational numbers. Do we think that's countable or uncountable? So what is a rational number? How is a rational number defined?
Rational or irrational?
Rational.
Is it fine as it could be modeled as two whole numbers?
Not whole numbers. Two integers, right?
Yeah, two integers.
So it's, yeah, so I guess, are those whole numbers?
Yeah.
I don't know if, so yeah, I haven't really heard whole numbers since like high school, I guess. So I forgot what they were. But okay, so whole numbers are integers. In that case, yes, it's two integers. So yeah, it's the ratio between two integers. So that's what rational numbers are. So do we think those are countable or uncountable?
Countable.
Huh?
Countable.
Okay, why? Why do you think? Or we can't prove it in this class.
Well, because it's a composition of integers and
How many
are
integers?
Infinitely many.
No, I mean one rational number. How many integers does it take to make one rational number?
It takes two.
And so it takes finitely many, right? Hmm?
No, I was thinking irrational.
Oh, no. Yeah, rational. So it takes finitely many rational integers to make a rational number. So it seems like it is countable, right? And we can think of it in terms of decimals as well. Say we take a rational number between 0 and 1. Well, at some point, it's just going to be 0, right? So after some point, it's not going to just continue to have non-zero terms anymore, right? So we can represent it. We can just cut it off at some point. We can represent it using finitely many digits. However, irrational numbers you can never represent using finitely many digits. You need infinitely many digits. So there are ways to prove these things, but we won't go through that.
Quick question. Maybe I'm wrong on this, but couldn't you say that since integers are countably infinite and radicals are a composition of integers, couldn't you say from that
it's actually a bit trickier than that. So Cantor has a proof for it, and basically what he does is I don't quite understand it fully, but he basically tries to draw out a map between the rational numbers and integer, or maybe natural numbers. But yeah, so it's a bit trickier than just saying that it's the composition of that. But you have to come up with the one-to-one correspondence basically, and that's the tricky part. It's a lot easier actually, in my opinion, to prove that the reals aren't countable, because there you try to create a one-to-one correspondence and then you show by contradiction that you can't. Whereas with the rationals, I think it's a bit more difficult. It's a bit more subtle, I guess. But he does have a proof on it, and you can look it up if you want. So,
Cantor, you said? Cantor.
Yeah, Cantor, yeah. So that's the idea of cardinality of sets, and this is going to be important for fractals. But before I tell you that, I should tell you something about the continuum hypothesis. So here, the cardinality is going to be, say, we'll write it as n here, but it's really written as aleph. I can't draw an aleph, so I'll just draw an n. And here, the cardinality is going to be 2 to the n.
Wait, what's an aleph?
It's a Hebrew / Arabic letter, although Arabic aleph is different from the Hebrew aleph, and I believe Cantor used the Hebrew aleph. So it's just A in Hebrew / Arabic.
Okay.
But yeah, so he showed, or someone showed, I think he did, but someone showed that the cardinality of the reals is 2 to the n, whereas the cardinality of the naturals is just n. So the continuum hypothesis says that there is no such set that has a cardinality between n and 2 to the n. So but it's a hypothesis. So you can either use it as an axiom where it's true or it's false, and your set theory there, or the sets you're dealing with, the theory would be consistent. And people have tried to prove this. So Cantor tried to prove it, and he actually went insane trying to prove it. Yeah. So and that kind of led to his demise. And then later, later in the early 1900s, Gödel, who showed that you can't prove everything, so he has the incompleteness theorem. So he showed that not everything can be proved in the simplistic sense. It's obviously, his incompleteness theorem is obviously a lot more complicated than that. But Gödel showed that, and then he tried to tackle a continuum hypothesis. And then he also went insane trying to prove the continuum hypothesis.
I'm seeing a trend here.
Not to try to prove.
Yes, don't try to prove the continuum hypothesis. Although we're applied mathematicians, so we would fail miserably trying to do that. So you probably don't want to tackle that problem. But yeah, so we don't know if it's true or not. So, and a lot of people have tried to prove it, and they haven't gotten anywhere. Yeah, exactly. So yeah, that's about cardinality of sets. But we're going to think of something a bit more concrete.
Would that be my final proposal?
I'll stick to that yourself.
Yeah, you might be better off.
So now we want to think of how this relates to fractals. So let's think of the Cantor set. And you guys know a bit about the Cantor set. So I'm going to construct it, and then we'll talk about some properties. So we take the unit interval. This is 0, this is 1. And then we're going to just take off that third. So let's say from here to, maybe that's a little too far. So let me just mark it here, actually. So I think this is a third. Does that look like a third?
Yeah.
Yeah, that's about right. So let's say from there, there. So you take off a third, and then you do the same thing on this interval. So you go ahead and take off this third, take off this third, and then you do the same thing on this interval. So then you have this. And then you do the same thing, so then you get this. So instead of drawing it like that, let me just draw it like this. So you get that. So you get something like that. So that's what the Cantor set looks like. And this is C0, C1, C2, C3, C4. So here I can only draw it up to 4 places. But on the computer, you can get it up to 7 places pretty easily. After that, the resolution kind of gets too small. But we can see that already at C4, it's very difficult to see some of these intervals. But then you continue doing this ad infinitum, and then the set you're left over with is your Cantor set. So that's the Cantor set, and it has some properties. It has some important properties. So it has complex patterns in arbitrarily small scales. So if we look at the final Cantor set, obviously we can't draw it, but if we look at that and we look at smaller and smaller scales, we'll see complex patterns even at the smallest scales. So you're not going to be able to zoom into a section of the Cantor set and see just an interval. You're going to see discrete points, and it doesn't matter how far you zoom in, you'll always see those points somewhere. So you're going to have some complex structure there. It's also self-similar. So if we look at, say, we wanted to, if we look at the entire counter set, then it's the same as looking at a third of the counter set. Because if you take this third, you have the same sort of process, right? So this looks exactly like C0, this looks exactly like C1, this looks exactly like C2, and that looks exactly like C3. So even if you look at the entire counter set, so say you took this off to infinity and looked at the entire counter set, and then just restricted yourself to a third, then you get the same thing. It looks the same. So that's that has self-similarity. And it doesn't have an integer dimension. So that's the tricky part. Let's think of that. And that's where we get into fractals. So if you take this off to infinity, what do you think you get? What are you left with?
A whole bunch of small points, like paths, I guess.
So points, right?
Yeah.
You're just left with a set of points. You don't have any intervals left because you took away all the intervals. So if you keep taking away all the intervals, all you're going to be left with are points. What type of points are they, though? Let me ask you that. Okay, so let's think of it this way. You're taking away this interval, right? And then you know that this point and this point will always remain. You know that this point and this point will always remain, right? Even here, like you know that this point and this point will always remain. Now we'll take off this interval. Then you know that this point and this point will always remain. This and this will, this and this will, this and this will. Same thing, you take off another interval. You know that these two will, 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 these two will. And then here, you know that every white point remains.
Is there one with 3 to the end?
Well, no, not a specific point.
Oh.
But what are those points called?
Epsilon.
No, no.
I'm trying to be productive here.
That's okay. So what are those, what points did I just point out there?
We go through like all possible points on the line.
Not quite.
I was going to say differentials.
Nah.
Trying hard.
So what are these 2 points called, 0 and 1? Endpoints, right? So you're left with only endpoints, right? So you see here, these 2 endpoints remain. And then you go down to the next level, and you see all 4 of the endpoints are going to remain. You go down to the next level, you see that all 8 of the endpoints are going to remain. Go down to the next one, and then every single endpoint here remains. Go down to the next one, every single endpoint here is going to remain. So the counter set is a set of all endpoints of these various intervals that you're taking away. So it's going to be the endpoints of these intervals for sure, but then also the intervals, the endpoints of the intervals that you're taking away. So that's basically what the counter set is. So it's just a set of all these, you can think of it as a set of all these endpoints. So there you don't have a straight line obviously anymore. You just have a set of points. So you might think it's 0-dimensional. But you also have some structure that you don't have with points, right? So if you take finitely many points, let's say you take that many points, right? Then if you say, look at this one little section, you're not going to see any more, you're going to see just one point. You're not going to see, you're not going to like see this entire thing anymore. But now if you look at the counter set, and you look at one section of it, then like a line, so if you take a line, right? And then you take some little section of a line, you still see a line. So that's why, that's like, that's one thing that distinguishes a 1D object from a zero-dimensional object, right? So you still see infinitely many points here. The same number of points that you would see here. So you don't see that with, say, finitely many points. But with the counter set, what you see is that it doesn't matter where you zoom in, you're still going to see that counter set. So there's something funny about this type of set. So that's why, I forget who came up with it, Mandelbrot, yeah. So Mandelbrot proposed that perhaps these objects have fractional dimension. So it's not that they're zero-dimensional, because they have some complex structure that zero-dimensional objects just don't have. But it's not that they're one-dimensional, because they don't have a length for this type of set. Obviously, we can look at 2D fractals and things like that. Or not two-dimensional fractals, but around two-dimensional fractals, approximately two-dimensional fractals. Whereas here, this is going from, say, something that's 1D to 0D, but it doesn't quite get to 0 dimensions. So the idea is it must have some sort of dimension between 1 and 0. So that's what we're going to look at. So now let's talk about dimensions of self-similar fractals. So all this started off with self-similar fractals. So self-similar fractals are a type of fractal where you can actually construct, or where you can derive the dimension in a fairly simple manner. So the idea here, and let's see if I want to do something else before. Yeah, so let's do that for the counter set first, and then we'll do it for another type of set. So here we're going to let n be the number of copies, and let r be the scale factor. So how much are we scaling this down by? So scale factor for each of the copies. Then we have something, but I won't tell you what that is just yet. Okay, so let's think of the counter set. So let's say we're going from the full interval into this interval, or into this set. So how many copies is created here? So we have two copies, right? So we have this copy and this copy. They look just like this, right? They're both intervals, so they look just like this, except they're scaled down by how much?
Third.
So a third. So here, n is going to equal 2, and r is going to equal 3. So it's scaled down by 1 over 3. So it's scaled down by a third, and we have two copies. Now, do you see a relation between n and r? Or a useful relation between n and r? So let's take a line, right? If we use a line, and we know a line is one-dimensional, so with a line, let's say we just copy a line. So we just copy the unit interval. So how many copies do we make if we just copy the unit interval?
1.
And how much are we scaling it down by?
0.
1.
Well, 1, right?
Oh yeah.
So it's scaled down by 1 because it doesn't scale at all. So then we see that if we have n equals r to the d, that d is going to give us our dimension, right? So for a one-dimensional object, we have one copy that's scaled down by 1, so it's one-dimensional. So here, So we're going to write n equals r to the d, where d is the similarity dimension. So this is called the similarity dimension. So this only works for self-similar fractals. So self-similar fractals are fractals that make copies of each other. So then we can see for the counter set, we're going to get something that's less than 1 dimension, but greater than 0 dimensions, right? So then this means that D is going to equal ln n over ln r. So that's how we're going to calculate the self-similarity dimension. So here, the dimension of this, of the counter set, is just going to be ln2 over ln3, which is clearly less than 1. So it's going to be a fractional dimension there. And we can do the same with some other fractals.
You can still have a fractal that's
Mm-hmm.
between, like, let's say 1 and 2, right?
Oh yeah, so let's do that. So let's take the von Koch curve. So there we start off with the unit interval as usual. So let me not put another mark there. So we start off with the unit interval. And then we're going to take a third of it. So kind of like the counter set, except we're going to draw a triangle on it. So it's going to be like that, and we're going to erase. So it's like the counter set where we're erasing that middle section, but then we add a triangle. And then we're going to do the same sort of thing. So we're going to have something like this. We're going to erase that. We're going to have something like this.
What's this one called again?
The von Koch curve. Something like this. And we can continue doing the same thing for each of those sections as well. So we see we're going from something that's one-dimensional, but now we're increasing the dimension almost. So if we continue this ad infinitum, we're going to get some sort of curve that has infinite arc length, which is weird, because how can a curve have infinite arc length? So clearly it's not going to be just one-dimensional. It's something that's a bit higher than one-dimensional. So let's go ahead and compute the similarity dimension of this. So what is n going to be in this case? How many copies are we making each time? We're not making 2. So let's think of. So we're making 4, right? So we went from a line. We took out the middle, but then we drew a triangle. So we have 1, 2, 3, 4 copies. So we had 1, 2, 3, 4. So that's why this is going to be 4. And then what's the scale factor for each of those copies?
1/3.
So it's going to be r equals 3, right? So then the dimension of that, so d is going to equal ln 4 over ln 3. So clearly this is greater than 1. And here the Cantor set is going to be less than 1. So that's the similarity dimension. That's the easiest dimension that we can deal with. And I should actually write down that this is von Koch curve. So that's the von Koch curve. So that's the easiest dimension we can deal with. But we don't always have self-similar fractals. So we need another type of dimension. So this is going to be the box dimension. So let's say that we cover a set with boxes so that we cover the entire set with boxes of size epsilon, but we're going to use a minimal amount of boxes possible. So we can do this for, say, this set. We can, if we took this off to infinity and then covered that set with boxes, and we just covered it with the minimum amount of boxes possible, size epsilon, then we can get a dimension for that. But it's hard to see with this. So let's think of the Sierpinski carpet, and that'll be there. The box dimension will come off very naturally. So this is what Sierpinski carpet looks like. So that's 0. So that's say S0. And then we're going to have S1. So this is just S0. So for S1, we basically fill in, and this is the non-similarity Sierpinski carpet. So with the regular Sierpinski carpet, you always fill in the center box. But now to make it, a non-similarity Sierpinski carpet, we're going to just choose a random box. So you guys choose a box to fill in. What box?
Middle?
No, other than the middle.
Top right.
Okay, so let's fill in this box then. So we're going to fill this box in. So that is going to be S1. So we fill that box in, that's S1. And then we're going to go to S2. Let me do that in a different color. So S2, we're going to do the same thing for all the other boxes that aren't filled in. So let's do that for this box. So now you're welcome to choose one middle box if you please. So what box do you want to fill in there?
Bottom middle.
Okay. So let's fill that one in. And then we're going to go here. So what box do you want to fill in there?
Top middle.
Okay. So we're going to fill that in. And then I'll just continue with the other ones. So in a lot of these, we have this theme of thirds. And it seems that that's a very nice way to make some of these fractals. So let's fill that one in, and then let's just go center for giggles here. And let's fill this one in. Let's fill this one in. And what else did we not fill in? We didn't fill it. We did. Okay, we didn't fill this one in yet. So let's fill that one in, and then let's fill that one in. So we're going to fill all those in. Now let's take it to another level. it's gonna get tough once I go. I'm gonna do, so I'll do this one. And after this, I'll do one more. Just so, I mean, it looks really nice, so. I'm gonna just do that. And maybe with all these colors, Ian can get some profound insight into something.
Well, that already happened when you were writing out the fruits. The
So-
colors.
Okay, maybe I can't continue it after this because everything's getting very, very narrow here. So maybe I'll just stop here with this level. Okay. So almost done. I could just give you guys a coloring assignment for this topic.
I'm down.
It'll be nice. Maybe it'll be easier to explain what I do to all my friends.
I'm just gonna do some coloring.
Well, I mean, coloring is a field in mathematics, right? Graph coloring.
I do want to. I should have majored.
Can I major in that?
You can, but it's very, very, very abstract stuff. So okay, let's just fill in some of these boxes. I'm just gonna
I
get some
majored in
random
coloring.
ones. Let's see there. Very hard to be random as a human being. It's easier for a computer to, well, actually it's not, because computers can't do random things. They have an algorithm that gets you pseudo-random stuff.
You know, the rand function actually
It divides two prime numbers.
yeah.
Yeah, I know.
It's not real randomness.
Yeah, I know. That's what I
It's
said.
fake random.
That's why I said pseudo-random.
Yeah.
I majored in pseudo randomness.
Yeah.
Huh.
I mean, it's kind of like chaos, right? It's just kind of pseudo randomness.
So, I hold the view that there is no real randomness in the world, even with quantum mechanics, and that we can actually explain things using pilot wave theory. But that's not a view that many people have. So hopefully some future employer isn't listening to this lecture.
What's pilot wave theory?
So it's the idea that things in the statistics in quantum mechanics comes out of trajectories of particles.
So it's
So
just
it's
chaos
deterministic.
theory applied to
Pretty much.
applied to
Exactly.
random cases. So
Yeah.
the statistics is just like an approximation of what actually is going on. But
Yep,
it can
that's-
actually be modeled using a chaotic.
That's the idea. since I am a dynamical systems person, I probably don't have too much to worry about. But if I was in physics, then I would be screwed.
Yeah, I work in the biophysics lab, and they never like my talk like that.
Yeah.
Because it's like the polite way of saying I'm sorry, but I think you're all wrong.
Well, I mean, it works for the most part. Approximately works.
Well, physics has always been an approximation.
That's true, yes.
Everything.
Fair enough.
And people just have different ideas on how to do things. I mean, physics, a lot of it is philosophy.
Well, it
So-
stems from philosophy.
Right. So I don't think we should just dismiss ideas that have scientific, that are, I guess, governed, that can be governed by science. I don't think we should say everything that's radical is outlandish. Okay, so.
I'm having a profound experience. I mean,
So that's gonna be S3.
can we have S4?
No.
Yeah, I was gonna try to draw it.
Oh,
Please.
no.
I didn't even know that.
So
I will draw it.
It would look really cool if we could do S4, but
Get a bigger
Could I
board.
I think that might be a waste of time because I spent
if
like
I look this up,
5
could I-
minutes doing that.
If
Wait,
I
what?
looked this up, like, could I find like higher and higher, like?
Well, sure. I mean, you can get a computer to do it.
Simulations probably the best way, right?
No, but I mean,
Yeah,
like,
there are plenty of simulations.
that's true, I guess.
Yeah.
I mean,
So you can get pretty deep into that. But probably not the best idea for a lecture because I don't want to be spending the entire time coloring.
I mean, didn't major math to be an art major?
That's true. Well, yeah, math is kind of a mix of art and science.
Well, it's art.
Well, applied math is.
That's why I
Um,
became an electrical engineer. I just like looking at
Mm.
input and output waves. They're so pretty.
So here, if we want to use the box dimension, we can cover the entire set with boxes of size epsilon. So let's think of S0. And let's say, so let's see how I want to do this. Okay, yeah, so we can basically cover these with boxes of size epsilon, and this is what the dimension is going to look like. So here, D is going to equal the limit as epsilon goes to 0 of ln n over ln of 1 over epsilon. So here, clearly, n, the number of boxes is going to depend on the level you're at, right? So here, we're going to need n as a function of epsilon. So let's think of how we're going to write that. So I can actually look in the book, I don't have to think of it. If I can find it, let's see.
Great thing about science, right? Other people have done a lot of the work.
Other people have done the work, yes. So, okay. Right, okay. So here we can think of these epsilons and then get an epsilon as a function of the small n. So here, this is S, say, n equals 4, or this is S0, S1, S2, S3. So this is S, n equals 3. So we can get a function of epsilon in terms of the small n, and we can do the same thing for the big N. So for S0, what is epsilon going to be if this is the unit interval? So the size, what's the size of the box that we're going to use to cover it? So let's say this is the unit interval, then that size is going to be 1, right? So there, epsilon is just 1. And n is going to also equal 1. There's only one box. Or there's only, yeah, okay, so yes, there's one box of size epsilon equals 1. So that's going to be S0. And then S1, so for S1, what's epsilon?
1/3.
So it's going to be 1/3. And n equals how many?
9.
It's not going to be 9 because we took this out.
8.
So it's going to be 8. And then for S3, not S3, okay. I messed up the colors there. But that's okay. So yeah, let's do S2 there. So what's S2? Epsilon is going to be what?
1/9.
So that's going to be 1/9, and n is going to equal,
64.
so 8 to the 8 squared, right? And this is 1/3 squared. And we can see this theme happening as we go down. So S3 is going to give us epsilon equals 1/3 to the 3rd, and n equals 8 to the 3rd. So that way we can find our box dimension for this. So here, n is just going to be 8 to the n. So we can take limit as n goes to infinity of ln, 8 to the n, over ln of 3 to the n. But then this is just the limit as n goes to infinity of n ln of 8 over n ln of 3. So then the n's cross out, and then we get that the box dimension is just ln of 8 over ln of 3. So that's how you calculate the box dimension. But there are some drawbacks to the box dimension. Obviously here it works well because we have boxes. But if you don't, if you have, say, something like this, it's not going to work so well. It's going to be fairly tedious to use box dimension, and for self-similar fractals, it doesn't make any sense to use box dimension. You could just use the self-similarity dimension, the similarity dimension. But yeah, so box dimension isn't used very much. So the only place you can use a dimension that is easy to get are self-similar fractals. But now, in chaotic systems, we're going to want to calculate the dimension sometimes, and we can't just use the box dimension for that, and we can't use similarity dimension because a lot of times in chaotic dynamics you don't get self-similar fractals. So we have to find a way to approximate a dimension. So usually for non-self-similar fractals, we're going to just be able to only approximate a dimension. So if we think of a phase space, and we're thinking of a chaotic system in phase space, we can get, say, strange attractors, which have fractional dimensions. They're fractals. We can get horseshoes, which are fractals. We can get period doubling. So when we look at period doubling, that's just going to be a fractal, right? So we just get a bunch of points, and it looks almost like a Cantor set for period doubling. So all these things are fractals. So let's think of something like this. So let's think of some sort of I guess like a phase space or some iterates, and let's say they look like this. So these are going to be iterates. So let's say they look like that. And let's take some ball of radius epsilon. So let's consider some x here. And let's take, or maybe I should put it inside. It's probably better off inside. So let's take an x here, and let's take a ball of radius epsilon about that x. So we look at some sort of structure. We're going to take a ball at that x of radius epsilon. And what we want to think of is if we run this map, let's say, how many iterates are going to be intersecting this ball? So that's what we want to think of. So then we can write this. So let n, but let me write it as nx. So here let nx be the number of points in b epsilon of x at each x then this nx is going to be proportional to epsilon to this d. So as we can see here, the number of points in this ball is going to change as we change the size of epsilon, right? And typically it's going to change with as a power law. So it's going to change as epsilon to the d. So it's going to be the number of points in a ball is going to be determined on epsilon, and it's going to be determined as epsilon to the d, where d is called the pointwise dimension. So then here d is called the pointwise dimension. So we can see it from here. But now we're not just interested in this. We want to see what we want to see what the dimension of that entire set would be. So we have this chaotic dynamical system, and we're looking at the phase space, let's say, and we want to see what the dimension of that entire set would be. So how do you think we should do that then?
Could you break it up into the infinitely amount of balls?
Okay, so that would be a way to calculate, so infinitely small balls,
yes.
but we can't do that in real life, obviously. So what we're going to want to do is do this sort of thing for a lot of different x's. So we're going to just average over many, many x's. So then we can come up with this. So let me write it as this. So if we average over many x's, we're going to get this. We're going to get, say, 1 over j, where if we sum over j for all the nx, j, then this thing is going to be proportional to epsilon to the d, where this d is called the correlation dimension. So in real life, that's how we're going to be approximating these fractals that come about in, say, phase space or in the iterates, in the plot of the iterates of a map. So that's the way we can approximate it, but of course, this can only lead us to an approximation. We can't get an exact dimension for this. So the only feasible place we can get an exact dimension is when we have self-similar fractals. That's the easiest way we can get an exact dimension for this. But an approximation is also quite valuable a lot of the time. So I should mention that there are times where you'll get some sort of system where throughout the set the dimension is going to change. So you have different type of fractals depending on where you are in the set. So that's called multifractals, and there the dimension is going to vary depending on your position x. But we won't talk much about that. I just wanted you to know that there can be these funny sets where you have some more complex behavior going on. So with that, we'll just end fractals, and next week we'll do our final experiment on the Chua stuff, on Chua circuit. Yep.
Oh, one more question.
Mhm.
So this technique, finding the correlation dimension,
Mhm.
you would normally apply that for something like, let's say, Lorentz equation?
Yep,
Simple.
exactly, yeah.
So how would you calculate the number of, since, I mean, n of x is essentially the amount of points inside the ball,
Mhm.
how would you calculate the number of points in that case for something like the Lorentz?
So Professor Blackmore would be able to answer this better, but I guess you can take a Poincaré section, right? And then calculate the dimensions there.
Yeah, the idea is you'd like to actually compute dimensions in something resembling a Euclidean space rather than trying to follow the trajectories around. Of course, you can, depending on what the trajectories are, if you know what the fractal dimension is in a, let's say, a Poincaré section, then you can sort of flow that dimension. So it adds another dimension basically.
I think I understand what you're
Yeah.
saying. You can get a general idea using the Poincaré section, and
Yeah,
then
so
from that,
like if you have Cantor dust,
extrapolate.
and then you draw a line through each of those points, let's say in the plane, then you're gonna have the dimension is going to be 1 plus the dimension of the Cantor dust. If it's sort of a two-dimensional kind of flow, it would be 2 plus the Cantor dust. Yeah, you try to simplify it by reducing the calculation, the essential calculation, to the lowest dimensional map you possibly can.
So any other questions on fractals or cardinality of sets? So unless Professor Blackmore has anything else to add on fractals.
Well, I came in a little late, so I don't want to ask any stupid questions. But of course, all of these various fractal dimensions that you're computing are all sort of hovering around the basic definition of a fractal dimension, which is the Hausdorff dimension. Did you say anything about that?
No, I didn't
That's
actually.
a bit
Yeah.
complicated. That's why it's sometimes a good idea to avoid that, let's say, for your first look at fractals. Because you have to look at coverings, and then you have to look at coverings of various diameters, and you get this sort of a critical value where the number either goes to 0 or it goes to something else, and that's kind of the Hausdorff dimension. So it's a tricky bit of business, but all of these things like box counting, correlation, and a variety of these other things are simpler, more computable versions of the Hausdorff dimension. In the simple cases, for example, the self-similar fractals, you probably did some of those simple calculations. Like you can use those to compute exactly the fractal dimension of a Cantor dust or the Sierpinski gasket or all of these sort of pretty things. It turns out that the similarity dimension turns out to be equal to the Hausdorff dimension, but proving that is not an easy thing. Some fairly nasty analysis goes on there.
So yeah, if there are no more questions, then that's it for today.